Hello again and welcome back. So in this lesson, I'm going to walk you through finding the horizontal asymptotes of different functions using a definition of limit that helps us to find horizontal asymptotes. And what we're going to do, we're going to use the limit as x approaches infinity of the function. Now, first thing I have to mention is that suppose we have a function f of x and it's represented by this kind of a form of p of x over q of x. This is a special case. Not all functions look like this, but for the purpose of the first couple of examples, I want to talk about the rational function. And suppose you have a setup like this where the numerator is a polynomial of degree n, and the denominator qx is a polynomial of degree m. Now, there are three cases that shows up, and if these three cases show up, depending on what they are, depending on the relationship between n, the degree n, and the degree m of this rational function, you will have different values for the horizontal asymptote. And remember, horizontal asymptote, the actual equation will end up being y equals to, because it's a horizontal line. Okay, so the first case is the n greater than m. That means the degree of the numerator is greater than the degree of the denominator. And if you have that, when you take the limit as x approaches infinity of that function f of x, what will happen is that you will end up getting, now in this case, I'm using just a positive infinity, but the negative infinity will be the same. So you will end up getting infinity. So the limit as x approaches plus or minus infinity will end up giving you plus or minus infinity. And in this case, you have no horizontal asymptote. Okay, that's case one. Case two, what if n is equal to m? And if that's the case, when you take the limit as x approaches plus or minus infinity of f of x, what you will get is the leading coefficient of the numerator or polynomial p of x divided by the leading coefficient of the q of x, which is the denominator. All right, so and that's very simple. So if you have the two leading coefficients are, let's say, 2x squared over 3x squared, and I'm just making this up right now, plus blah 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 plus other terms. When you take the limit and the other x approaches plus or minus infinity, you will end up getting 2/3, because the leading coefficient here for the top is 2 and for the bottom is 3. Let's look at case 3. And case 3 is when the degree of the numerator is less than the degree of the denominator. In this case, when you take the limit of the function as x approaches plus or minus infinity, it leads to 0, and y equal to 0 becomes the horizontal asymptote, right? And on top, by the way, I forgot to mention this, so this is y equals to 2/3 becomes the horizontal asymptote in this second case. All right, now we're going to go through and we're going to look at few examples. I've got 3, 4, 5 of them. So let's go through each one. Okay, so here's the first function. We're going to take the limit of the function as x approaches infinity. In this case, we're just going to do infinity because they're both the same, negative infinity and positive infinity. So to do this, first you have to double check to make sure the degree of the numerator and denominator are based on one of the three cases. In this case, we have 1 and 1, so that means that n is equal to m. Okay, both degrees are the same. And in this case, what you will do, you have to divide. And in all cases, you do the same. It's just a typical limit calculation that you have to do. You divide all terms by the highest degree term, and then you go through and solve. So in this case, 2x divided by x plus 5 divided by x, that's for the numerator. And for denominator, you do the same, 3 divided by x minus x divided by x. Very good. Now we're going to do simplification. So we take the limit when x approaches infinity of now new fractions that we have created. Okay, and then we're going to go through each one, and here it is. So this is very straightforward. You take the limit of each of these terms, and you notice that first of all, before we do this, we can simplify. Let's simplify, and x cancels out. You get 2 plus 5 over x divided by, and then 3 over x minus 1. Okay, and now we can employ the uh, limit. Now 2 stays 2 on top. That's not going to change. For the second term, 5 over x. X approaches infinity, so 5 over x, 5 divided by a huge number that becomes closer to 0. So that's 0 over. We do the same thing with the 3 over x. 3 over x, x approaches infinity. This value 3 over huge number, that is 0, and then -1 stays -1, so the answer in here is -2, and so the limit of this function as x approaches infinity is -2. That means what? That means this is the equation of y equal to -2 is the equation of the horizontal asymptote. Great. Let's look at the second question. Here's the second question. We have this function g of x. So we're going to take the limit as x approaches infinity of the function. The first thing we have to do, we have to make sure that we know the effective degree for the numerator and denominator, and then apply one of the three cases. In this case, we have x cubed on top and x in the bottom. That means the degree of the numerator is greater than degree of the denominator. So we know that n is greater than m. So now that we know the effective degree of the numerator and denominator, we can go ahead and divide all the terms by the term with the highest degree. So let's do that. So we have limit at x approaches infinity. The function, we're going to divide every term by the x cubed for the top, and we're going to do the same thing to the bottom, and realize that this entire thing, we're going to take the limit of that for each term and then rewrite. Okay, so we know that. Let's simplify. So when you simplify, you will get this. Just divide x cubed by x cubed. For each of these terms, you have to be dividing. And then when you have a common factor, you have to divide. And then you take the limit of each of the terms. So start with the top. We notice that 1 over x cubed as x approaches infinity, that's 0. That is 0. Okay, 3 over a huge number comes closer to 0. The top will stay at 2. The denominator, 2 over x squared, that is 0. X cubed, 3 over x squared as x approaches infinity, that would be 0. So you get 2 over 0. And 2 over 0 is infinity. Okay, in this case, is infinity was undefined. That means no horizontal asymptote. Okay, now another intuitive way without going through all of this, I mean, obviously you have to show this. If a question like that shows up, you have to show all your processes. But the more common sense is that you're looking at the effective degree of the numerator and denominator. Notice that the numerator actually dominates the behavior of the function, and for the numerator is that, but it's actually for the entire function, because the denominator effective term for the denominator is the 3x. Okay, so in this case, you can easily say that as x approaches infinity, 2x cubed becomes larger and larger, closer to infinity, huge number, in comparison to 3x, and therefore the answer to this limit will end up being infinity. And that is because 2x cubed over 3x will end up getting closer to infinity as x approaches infinity. And therefore this function has no horizontal asymptote. But what it will have what is called as point discontinuity based on the denominator. So this is the denominator. Let me bring this down. The denominator 3x plus 2, what is the restriction for the denominator? Well, in this case, x cannot be, you set that equal to 0, and you realize that x cannot be negative 2/3. Well, when g of x is g of negative 2/3, the value of the input x, negative 2/3, when you plug into the function, you get the value for y. There is a point on the graph of this function, which whatever it is, that point is a discontinuity point and is a removable discontinuity point, but it is not a horizontal or vertical asymptote. In this case, no horizontal asymptote. So whenever you have a situation like this, you could have a removable discontinuity point on the graph. Let's do question number 3. Here's question 3. We're gonna find if this has any horizontal asymptote. So we're gonna go through. First, we're gonna check the effective degree for numerator and denominator. In this case, we have the numerator has a degree 1 and denominator has a degree 2. So in this case, n is less than m. Okay, and if that's the case, we know what will end up being y equal to 0, but we're going to show it algebraically and through the limit. So when we do that, we divide every term by the term with the highest degree, which is x squared. All right, so we divide everything, and then each term has to go through the limit calculation as x approaches infinity, and then we're going to find out what that is. So the first thing, let's simplify. And here it is. So I went through x over x squared is 1 over x, and then 3x squared, and then x squared over x squared is 1. X over x squared is 1 over x, and 1 over x squared, you just leave it alone with a negative. And now we apply the limit as x approaches infinity to each term. So you notice what will happen. Here we have, so 1 over x squared, that's 0. 1 over x, that is 0. Okay, 1 stays at 1. The top, 3 over x squared, that is 0. And then 1 over x as x approaches infinity, that is 0. You have 0 over 1, which is equal to 0. And that is y equal to 0 is the equation of the horizontal asymptote for this function. All right, let's go to the next example. So here's question number 4. This is actually a good question because it's going to challenge you to think about it a little bit differently. But at the end of the day, we're going to follow those 3 cases again. We just have to make sure we understand that what is the effective degree for the numerator and denominator, and it follows within the 3 cases, we're going to go through the same processes. Okay, so the very first thing we need to focus is that the term for the numerator that actually impacts the numerator is the x cubed, is x squared, and is a cube root of x squared. Okay, don't worry about the plus 8. That's not as important. In this case, the exponent, the effective degree is 2/3. Okay, so that's the manipulation you have to do. What is the effective degree for the denominator? Well, for denominator, that's very simple. So this is for the numerator, and the effective for that one is x. X is 1, so that's x equal to 1. That's the denominator degree. Excellent. Now, between the two, 1 or 2/3, which one is bigger? So 2/3 is smaller than 1. That means the numerator is less than the denominator. And then we're going to employ the same technique in one of the cases, and it should give us, in this case, it should give us 0. That means the horizontal asymptote will be y equal to 0, but let's go ahead and prove it. We're going to do the same thing again. Now, here's a trick. You have to divide everything by the highest exponent or highest degree term, but when you do this, you have to be aware that cube root of x cubed is x. That's what we are doing here. Okay, so when we go through that, we have to use that instead, not just x. So we have the limit expression written of the function. We divide everything by the cube root of x cubed, which is equal to x. We established that we have to divide the top and the bottom of every single term by the highest term degree for the function, and that's x to the 1. So that's what we're doing. But remember, in the situation like this, you need to make sure you're actually modifying the value so that it shows up as the cube root. So cube root of x cubed, you divide the denominator by x, that is already there, and then now we're going to simplify. So as you're simplifying it, make sure you pay attention to the radical rules and everything. So the top, everything goes under the radicals, and then rewrite. So you will get this simplified form of this expression, this function, okay? So I just use the radical laws to go underneath as a division, simple as that. And then x divided by x is 1, and 2 over x, 2 over x. And now we're going to go and simplify more, but you realize that from this point on, it's just algebra. So let's simplify it. So we have this simplified form. Now we're going to employ the limit function x approaches infinity for each term. So let's go ahead and see. We have, let's start with the denominator, 2 over x as x approaches infinity, that is 0. 1 stays 1, that doesn't change, so that is our 1 in the bottom. The top, x 8 over x cubed as x approaches infinity, that is 0. 1 over x, that will end up being 0 as x approaches infinity. So the top you'll get 0, and then denominator is 1. The answer is 0. So y equal to 0 is the equation of your horizontal asymptote for this function. Yes, for this function right there. Okay, one more example. Okay, this one is a special one. I put it in there just to make sure that you are paying attention. So here is the function. It looks like a square root function. I want to know if this has any horizontal asymptotes. So the first thing that you got to do, you got to find out the effective degree of this, what you can call it, a function. Well, the effective degree is square root of x squared, which is x, which is 1. Okay, that's the effective degree. So, but that's not a rational function, that's a square root function. So two ways you can go through and find out the limit. One is by intuitive deductive reasoning, and that is that the value or the variable that makes a difference for the behavior of this function is x squared and x squared. So if you have square root of x squared minus the square root of x squared, because the plus 1 inside the radical and the negative 1, that's not going to change anything when x approaches infinity. That's negligible. Well, what is that? Well, this square root of x squared minus x squared of x squared is x minus x. Now, you take the limit as x approaches infinity of x minus x. Is a silly way to write this because you could just say that's 0, which is true. Well, that is 0. That doesn't apply anymore. So x minus x 0, so limit as x approaches infinity of 0, well, it's 0. So the answer to this one will be y equal to 0. That's the equation of the horizontal asymptote. Now, there is another way of doing this question, and that is you have to use a conjugate and go through the limit process without the intuitive way. And then we can do that as well. We can do that. So the second method is this. We take the limit x approaches infinity of this function, but we multiply it by conjugate of this radical function, but radical expression. Now the conjugate of this is the same, but you just change the sign. Okay, that's plus. Everything is the same, but you can just multiply anything you want. You can multiply anything by 1. That's not going to change the value of function. So now you have to make sure that you're multiplying it by the fraction that is the conjugate on top and conjugate of 1, because this entire thing is actually equals to 1. That's not going to change anything. Now you're going to go ahead and multiply through and do some simplification. And it's just basically multiplying the top, multiplying the bottom, and rewrite. So limit as x approaches infinity, the top you will get x squared plus 1, because difference of squares, x squared, sorry, minus x squared minus 1 all over, and then square root of x squared plus 1 square root of x squared minus 1. When you get that, you can notice that you can easily simplify x squared minus x squared. That's 0. And on top, you will get 1 negative 1. So that would be 2. So you have 2 here. And then denominator, you're going to leave it alone. And now we're going to divide everything by the square root of x squared, which is x, but inside the bracket. So let's do that. So now we know that we have 2 on top, and we know that the effective degree of the term in the denominator is x, so we have to divide by square root of x squared, which is x itself. So 2 over x, we divide the top, the numerator, and then denominator, each term you divide it by x squared, because in fact this is x, and then you simplify, and then you go from there. So let's do that. All right, so when you do this, you'll get this new expression, and then we're going to employ the limit as x approaches infinity. The top 2 over x as x approaches infinity, that is 0. So we have 0 on top. Let's look at the denominator. 1 over x squared, that is 0. You got 1 left. And also, this is 0. 1 over x squared is 0. And then square root of 1, and you have 1 plus 1 in the denominator, and then your final answer will be 0 divided by 2, which is 0. So the equation of the asymptote is y equal to 0. That is the equation of the horizontal asymptote. All right, and as we expected using this deductive reasoning right at the top, when we said that it should be y equal to 0, and we got that. Okay, all right, I hope you found this useful. Check out the next video about limits, derivatives, and see you in the next video.